Welcome to the walkthrough video of week 7, problem 1.3. We are continuing on counting problems. So for this problem, it is the classical variation of the balls and beans problem, and we will delve into it deeper in this video. So how many ways are there to distribute n red balls? N blue balls, both balls are indistinguishable among undistinguishable beans. If the order in which the red and blue balls are placed in the container doesn't matter. So in this problem, there are some terms we need to explain. The first thing is distinguishable and indistinguishable. And the second thing is the order doesn't matter. The order doesn't matter. So what does distinguishable and indistinguishable mean? So it means that for the beans, for example, we have bin 1, bin 2, and bin 3, right? If the beans are indistinguishable, so in this case, if we have red balls and blue balls, if we have one red balls here, and let's say one blue balls here, and nothing in the bin 3, it is equivalent as one blue ball in bin 1, one red balls in bin 2. So if the beans are distinguishable, it means that we can just like arrange the beans in any way, and any of the arrangement should be seen as a single arrangement, because you are like, in this case, you are not able to distinguish bin 1 to 3, right? So these two combinations just look the same. So this is the case when beans are indistinguishable. In the distinguishable case, we are actually labeling the beans. For example, we are labeling the beans at 1, 2, 3 and 1, 2, 3. So in this case, we can tell these two kind of arrangement are not the same, because in the first case, we have a red ball in B1, but in the second case, we have a blue ball in B1. So this is distinguishable, and we are dealing with the distinguishable case. The second thing we need to explain is about the red balls and blue balls are indistinguishable. It means that so like if the balls are distinguishable, then which means that we can actually label the balls. For example, there's a ball called 1 and there's a ball called 2. Hold on. Yeah, maybe there's a ball called 1, there's a ball called 2. And in the second case, we just like switch the order. So if the balls are distinguishable, then these two cases are not the same, because the balls are labeled and you can see that the red balls are matched with different beans. On the other hand, if they are indistinguishable, then all the red balls are just the same. So yeah, you cannot tell the difference between the two cases. So that is what distinguishable and indistinguishable mean. And we are dealing with indistinguishable balls and distinguishable beans. So another notice is, what does the order doesn't matter mean? It means that whether we place the red ball first in a bin and then the blue balls, or if we place the blue ball first and then red balls, like the orders of the balls inside the bin doesn't matter. We just care what balls are in what bin. So then we can just go through some details of this question. The first thing we notice is that the red balls and blue balls doesn't really affect each other, because we are just distribute n red balls and n blue balls into the bins, and whether the red balls are distributed shouldn't affect how the blue balls are distributed. So they are kind of independent, which means that we can deal with each case once and then combine the two cases. So let's first deal with the red balls. So right now the problem is simpler. We have n balls and n beans. Right now it become a really classic balls and beans problem, right? So how to solve it? So because the beans are distinguishable, we can make the beans, we can label the beans as 1, 2, 3, all the way to n. And because the balls are indistinguishable, we can just place the balls in a row. We want to put the balls, and suppose they are n balls. Because we need to put the n balls into n beans, we can think of just like we are dividing the balls. For example, which is that we are putting bars inside the balls. For example, if I put a bar here, then this is the first bar. Then, what is in front of the first bar became the balls in the first bin. And then I place the second bar, and then what's between is becomes the second bin. So the trick here is that instead of just putting the balls into the bins, we're dividing the balls in a row using the bar. And what's between the two bars are the balls inside the bin. Because we have n bins in total, so we need to have, let's just like arrange some bars. We have n minus 1 bars. Because we want to have n intervals, so we need n minus 1 bars to just divide the n intervals. So right now the problem is much simpler. It becomes an arrangement problem. Oh, and also I have to notice like some edge cases you may think of. For example, if like two bins are placed together, then there's just 0 balls here. Or in some extreme cases, maybe in the front you have all of the n minus 1 bins. You have all of the n minus 1 bars and all of the balls are after it. What it means is that you have all of the balls in the last bin. So for those extreme cases, you can still extend the balls in bin. And that is why it is a correct approach to solve the problem. Okay, so after understanding the balls and bins, the problem is a simpler arrangement problem. We have 2n minus 1 because we have n balls plus n minus 1 bins, n minus 1 bars. And we just need to arrange the 2n minus 1 thing. And the possible arrangement is just like choose, because we have 2n minus 1 positions in total, and we need to choose n positions for the balls. So it becomes 2n minus 1 choose n. So that is all of the possible distribution for the red balls. Because we know that the red balls and the blue balls, then let's consider the blue balls. Because there's no difference between the red balls and blue balls besides their color, so the answer should be the same, which is 2n minus 1. Then we can think of like combining the two cases. Because for every distribution of the red balls, it can be matched with any distribution of the blue balls. So we need to time these two things together. So the final answer is 2n minus 1 just n squared. Because you can think of like just each element in this one and this in this one and this one. Each element inside can be matched each other. So we actually need to time these two answers together, which gives us a square. Yeah. So this is problem 1.3.